What's going on, everybody? It's Mr. Gust, and I'm back in the physics classroom. Today, we're going to be trying to answer this question here. How can I measure unknown forces like friction and other unknown forces that I can't directly measure? So we're coming here. We just spent some time outside pushing the truck around. We just pushed the truck around. We had to figure out the mass of the truck by simply pushing it. And one of the big issues we had with that is that there's friction in the truck. There's friction in the axle and the tires between the trucks. So there's this friction happening, not necessarily on the ground sliding, but there is friction in that system. And so we had to somehow determine that because we didn't have some kind of fancy, expensive device that I could plug into the truck and say, hey, here's the amount of friction in the axles. So because of that, we had to rely on some tricky physics, some well thought out physics that helped us find and measure friction and other unknown forces. So what we're going to do today is a little example here in the classroom where I've got a block, a friction block, that's here in front of me. I've got a spring scale here, and we're going to look at a couple of forces that maybe we can't directly measure, but we're going to use some tricky physics here to figure out how we can determine some of these unknown forces, okay? So the first unknown force that I want to figure out, well, first of all, what I want to do is put this block on the surface right here, and let's just look at this block and model the forces acting on it, because right now there are probably two forces acting on it if I think about it. So let's go ahead and model it. So when this thing is sitting here at rest, here's my block. As it sits here at rest, the block is on the planet Earth, so we know there's a gravitational force or a weight force acting on it. But because it's sitting on the table right here where it is, we know there's also a support force, some kind of force from the table pushing back up on the block. And we call that force, because it is perpendicular to the surface, we go ahead and we call that a normal force. And the question here is, I don't right now have a normal force measuring device, so I wonder, what is the normal force? What is this equal to? How can I determine the normal force? And I hope this is a pretty straightforward problem for us, but if I look at this object sitting here on my surface and I wonder, what's the normal force? Well, I don't have a normal force measuring device in front of me. I only have a spring scale, which will pull things and allow things to hang from it. So let's do this. Let's first say, as it sits there, let's write an F net expression for this object. So we can say the F net force, in this case in the y direction, is equal to m times the acceleration in the y direction. We always start with Newton's second law because Newton's second law is always true. Even if forces are balanced and there's no acceleration, this is always going to be true. Then we go ahead and we write all of the forces that are in the downward direction or the upward direction. We pick one first. All forces one way minus all forces in the other way. I'm going to say Fn is upward. Let's call that positive. That's the only upward force, minus any downward force, and that's just Fg. So I'm left with this expression here. Given this, what I end up seeing is that, okay, the block sits on the table at rest. There's no acceleration there. Therefore, 0 newtons is the net force. So I can go ahead and write it this way. And then lastly, what I find out is that actually Fn is equal to Fg. Okay. So even though right now I don't have a normal force measuring device, if I had a way to determine the weight force or force of gravity on that block, I would be able to determine this unknown normal force, even though I can't directly measure it. I can measure weight and in turn determine normal force. So given my spring scale and my block, I know from earlier labs, all I have to do is hang this block from my spring scale and get a reading. And when it does hang, we're looking at right about 1 Newton. Okay, this thing has a weight of 1 Newton, and because it has a weight of 1 Newton, because Fg equals 1 Newton, that means that my normal force must be 1 Newton. Now, yes, this is very easy. I hope this is very straightforward. You're like, Mr. Gustin, I didn't need you to do 3 lines of algebra to determine this for me. I'm doing this to set up something that might be a little more complex, something that might seem a little more tricky, something we may have done with the truck outside. So let's do this. Now, instead of just having this object resting on the table, what about pushing it across the table? If I take it and I push this thing across the table at a constant velocity, or even at an accelerating velocity, then what forces are present? let's take that into account. Let's do two things here. Let's go ahead and say at a constant velocity first, constant velocity, and then we'll do constant acceleration, okay? So at a constant velocity, let's think about the forces that are present as I push this thing across my table at a constant velocity. When I do that, Fg and Fn are still present, and I'm also pushing. We can call it F push or Fp. But if these are the only forces present, then the push force would cause this block to accelerate across the table, not move at a constant velocity. So there must be some kind of resistive force, some kind of force acting against the push force. And most of you are very quick to say, Mr. Gustin, that's friction. And you're right. There is a force of friction resisting my push force. That's what keeps this thing at a constant velocity and keeps it from speeding up across the table. So let's go ahead and look at this. Now, my question really is, if this is what's going on, I know Fg, I found that. I know Fn from my previous situation. I can probably measure push force or pull force directly by simply attaching my spring scale to this and pulling this across my table. Like, I've got a pretty easy way. I should probably make sure I pull this horizontally and not at an angle. We're not doing components yet. But like, if I pull this horizontally, I can measure the amount of force I'm pulling with, but can I measure friction? Like, I can't measure friction. I can't slide something under there that measures the amount of friction between the two surfaces. So our next question is going to be, what is force of friction equal to? I don't have a tool to measure this, so I'm going to have to use my tricky physics, my understanding of physics concepts to determine friction, not measure it. Let's go ahead and write an F net expression for the forces in the direction of friction. In this case, that's F net in the x direction. It's equal to mass times the acceleration in the x direction. And in our case, there's the push force in one direction. We can subtract the resistive force of friction. Now, it's important that we're moving at a constant velocity. And I'll show you why in a second. But because we're at a constant velocity, this acceleration is 0. We're not speeding up or slowing down. It's a constant acceleration, which means 0 newtons is my net force. So force push minus force of friction equals 0. And aha, we see this interesting concept again, where the force of push or pull, whatever force I'm applying of this brick to move it, is equal to the force of friction because there is no acceleration. Because I'm moving at a constant velocity, this statement is true, which means if I go ahead and I pull this thing at a constant velocity perfectly horizontally like I should be doing, and it moves at a constant velocity, I end up with like 0.25 newtons of force. That means that because my pull force is 0.25 newtons, that my friction force in this case between the block and this table is also 0.25 newtons of force. I have just determined what friction is without having a tool to directly measure friction. I simply use my understanding of physics to do so. Now let's see what happens with a constant acceleration. Can I do this thing with a constant acceleration? If this thing accelerates across the table, can I determine the force of friction? Let's find out. Well, if it does accelerate, we can draw our FBD. There's still FG. There's still Fn. We know that those two things are equal. And I'm going to pull now with a pull force, and there's still going to be a friction force acting here. I'm not exactly sure of the magnitudes. Let's just draw them out and see what happens. But I'm assuming in order to get it to move at an acceleration, I'm probably going to have to pull harder than I did before. That's because it's going to accelerate, not move at a constant velocity. Let's go ahead and write the forces that are in the direction of this friction that I'm trying to find. All right, so we're going to ask ourselves again, what is the force of friction equal to? And can we solve it in this scenario? Well, F net x is equal to ma in the x direction, which is equal to the forces that are there. We have the pull force in one direction, and we have the friction force in the other direction. So let's go ahead and check this out. If I go ahead and pull this thing at a constant acceleration, let's see what kind of force we can produce here. Okay, as I accelerate that across the table, let me try that again. Make sure I accelerate it. I'm not sure I accelerated across the table. All right, when I accelerate across the table, I get a force of 0.45 newtons. So I get 0.45 newtons. Wonderful. I can go ahead and plug that in for this. MAX equals 0.45 newtons minus the force of friction. Well, hang on, folks. Now I'm stuck, right? I want to find force of friction over here. I know my pull force. I can easily measure that. I just did. But I just don't know what the mass is. Could I find mass? I certainly could find mass. I could go ahead back over here to my FG statement and find the mass. Wonderful. I could use my FG equals mg equation to find mass and plug that in. But ultimately, I don't know the acceleration. And because I don't know the acceleration, and because I cannot determine acceleration with the spring scale alone, I end up with an equation with two unknowns in it. I cannot simply accelerate an object to determine the force of friction. It's not going to work for me. So, where is this sneaky trick? If I look at my three scenarios, the sneaky trick we're using here is when accelerations are zero, when either constant velocity is occurring or rest is occurring. In both of these cases, we see balanced forces. We see zero net force. And because of that, we can use other tools like spring scales or bathroom scales from the car push lab to find unknown forces. To answer our big question, to go back where we started, how can I measure friction or other unknown forces? Well, it all starts with moving at a constant velocity. See ya!